Good afternoon. My name's Corrie Elston. I'm the CTO Financial Services for Google Cloud Platform. We're very lucky this afternoon to have Matt Taylor with us. Matt's the CTO of Kensho. Now, Matt's going to do a proper introduction to himself and to Kensho in a few minutes, but I just wanted to start off by saying that Kensho's an extraordinary company that's pioneering real-time statistics and analytics, machine learning for financial services. Now, Matt and I this afternoon are going to talk about Kensho on Google Cloud Platform, machine learning in your browser. And we got a real treat because Matt's come up with a custom TensorFlow machine learning model based on Kensho's data that he's going to demonstrate for us. Now, we're going to split this presentation into two portions. I'm going to lead off relatively quickly, and I'll tell you about why Google Cloud Platform's the best place for you to do your analytics and machine learning. Not just a good option or a good place, but the best place for you to do those activities. Matt's then going to take over, and he's going to talk about Kensho and their machine learning. But I just realized I made a mistake. When I was preparing for this, I didn't sort of take into account that we'd be doing it right early in the afternoon. So how was lunch for everybody? A good lunch? Everybody get ready for the sessions this afternoon and San Francisco this evening? A thumbs up for lunch? All right, so I sort of transparently recovered from my mistake, and now we can go on to some machine learning. Modern machine intelligence, a branch of computer science that builds systems to perform similar functions to human intelligence, such as learning, reasoning, self-correcting, and adapting. And it allows us to do some astonishing things. Just within financial services, which is my specialization, it allows us to manage risk much more effectively. It allows us to surveil activity much more effectively. It's, in essence, it promises to be the piece that was missing for so long, where people thought that financial markets were so inherently complicated that they couldn't be understood. But you've seen, again, you've seen the presentations where machine learning, TensorFlow, Google Cloud Platform give us the opportunity to bring that understanding to very high dimensionality data. And of course, the caveat is that there's more and more data. The amount of data is increasing exponentially. The need to make use of that data is becoming ever more pressing. So we need to scale, sometimes enormously, and we also need to move very quickly and experiment and break stuff very regularly. And that's where Google Cloud Platform comes in, to give you scale and the ability to iterate. Which leads us to a premised architecture for analysis and machine learning. I'm not going to spend much time at all going through the boxes on this slide, apart from saying that each of these services is fully managed, no operations. Each of them offers best functionality, wonderful price, and performance. What I do just want to spend a couple of minutes talking about are the things that I've built over the last 12 to 18 months using these building blocks, because that's where the rubber really hits the road. And that was the context that I wanted to share with you. What I've done can inform what you're going to build going forward, and hopefully it will inform what we'll build together. Number one, I built a proof of concept using Dataflow that took 10,000 30-year time series of financial data and correlated everything by everything. 50 million correlations of 30 years worth of data, 3 minutes at 300,000 correlations per second, compared to running it on a 16-core server, where I turned it off after 12 hours because it was just, if it doesn't finish in 12 hours, that effectively sort of goes towards infinity to me. It was very boring to wait for it. I built a proof of concept using PubSub, Dataflow, Cloud Storage, and Bigtable that ingested a simulated market data feed of all North American market data in graduations of 250,000 events per second. Did that from PubSub, and I also did it as files. Took about 2 days to code that up, and it took 0 overhead in setting it up and bringing it down. Interestingly, I also built Spark clusters to do a grid search of that data using Dataproc. Those clusters of 25 servers took less than a minute to come up, took about 45 seconds based on my testing, which means I was able to do that grid search by instantiating and then tearing down whole clusters of machines. Finally, and recently, we built a machine learning model that spanned Spark ML and TensorFlow to put an ensemble together to see how those things worked. And with that, I wanted to hand it over to Matt, who's going to talk about what Kensho's doing. Thank you very much.
Thank you, Corrie. Thank you, Corrie. Our partnership with Google on GCP has been a real pleasure. And I think one of the things that attracted us to Google was the collaborative nature in which we get to develop our products. He's also done a fantastic job of kind of showing off the raw power that GCP provides to us. So today I'm going to give you a personal look under the hood of Kensho, what our mission is, how we think about the world, and most importantly, we'll walk through a machine learning experiment together, letting the computer identify what days are like this. So Kensho is a high-end analytics platform for the financial industry. Think machine learning-powered hedge fund analytics delivered via the browser. If you work at a major bank or a major hedge fund, you're probably already aware of our platform. If you've watched CNBC, you've likely seen the Kensho Stats box, where their anchors use our platform to analyze events in the news. While we deliver hedge fund caliber analytics, we're not a hedge fund. And that's one of the nice things that I can do today is, as a startup, as a technology company, I can come and give you a peek under the hood of how we treat financial analysis. This is making sophisticated financial analysis more accessible, intuitive, and beautiful. Now, as part of a Kensho team and a back-end nerd, data nerd at heart, I'm passionate about deleting code and using technology to understand the world. Machine learning accomplishes both of these goals. I joined Kensho in 2013, and I now quarterback the engineering, data science, and design teams. And every day, I rely heavily on my experience building low-level financial infrastructure, high-frequency trading, and delivering millions of cat GIFs at Tumblr. Kensho and our machine learning on Google Cloud Platform is the unity of these goals. Make it smart, make it fast, and make it beautiful. Now, founded in 2013, Kensho, like any almost 3-year-old, we're curious about the world, we come with few preconceived notions, we're eager to learn, and we adapt quickly to new information. We do this via search, discovery, analysis, knowledge graph, event database. We deal with single assets, macro events, geopolitical, weather, and today we're going to ask the machine to identify days like this. So like any good experiment, we are going to start with a testable hypothesis. We're going to plan for our experiment. We're going to structure a specific test. And we're going to let the machine drive our analysis. Then we're going to feed it back into the Kensho platform and see how the markets react. So if you've read A Random Walk Down Wall Street and believe in efficient market theory, you probably think that the answer is no. If you recall the financial crisis and the Great Recession, you might think asset prices can be grossly mispriced for prolonged periods of time. You might think the answer is yes. Using market, events, and other features, can I gain insight into what may happen tomorrow? Let's find out what the computer thinks. In order to maximize learning, there's 2 things that we really need. And for hungry, lean companies, the most important question is, what is the most valuable thing I can learn right now? And the 2 things I need are resources and proper timing. So I want to take a step back for a second and talk about those 2 things to make sure now is the time to act. Now, for resources, I borrow a lot from the same challenging questions that face our own education system about educating our best and brightest to keep America competitive and across a global marketplace. You need physical safety to explore and experience what the world is around you. You need resources to fuel and encourage and to grow with you. You need a community of mentors, guides, and helping you correct your mistakes. You need a culture that encourages you to learn from mistakes, to try lots of things, and to fail quickly. But above all, you have to always be learning. And if we apply this same approach to how we teach our machines, and then how our machines teach us, right? Data center security, CPU, disk, and network capacity, unparalleled access to APIs, data, the right permissions to not do the wrong things, we can do a really powerful stuff that becomes a tipping point in the ecosystem where it feeds back onto itself and becomes a multiplier. Now, the second thing we need in addition to resources was timing. And this is critical. And one of the things that struck me was thinking about one of my favorite things in all the world, the Large Hadron Collider. It took 10 years to build it, 10 years, from 1998 to 2008. It was a significant international collaborative effort by CERN. It needed years of theoretical testing and at smaller attempts to build smaller colliders. It didn't have its first test run until 2010. But it all paid off. Right? In 2012, they discovered the Higgs boson and is now being used to measure some of the highest energy collisions in the world. I want to compare that to what Kensho gets from GCP. Instead of investing a generation of knowledge and science, and instead of investing a half-decade of infrastructure build-out and another decade to actually get it running, we spend minutes. We measure our scientific process in minutes of time and money. Founded in 2013, we use machine learning on GCP to power our platform. Now, what struck me at this is Google was founded in 1998 as well, the same year they started building the Large Hadron Collider. And while we can run countless experiments every day and scale up those experiments to the largest in the world, I asked myself, why are we able to do this? How can we go from a generation of planning to doing science and data science and research and machine learning in minutes? We're standing on top of the other thing that started in 1998. Google has more than a decade of building out infrastructure, security, data expertise. And it struck me at yesterday's keynote, Diane Green mentioned that Google spends $9.9 billion every year on CapEx. And it cost approximately $9.9 billion to build the Large Hadron Collider. So we are standing upon the Large Hadron Collider equivalent of cloud computing. And that means we can start signing customers, solving our problems, and doing machine learning without having to build 17 miles of tunnel underneath Europe. So if we have resources and we have the timing is right, because we can do our experiments measured in minutes, and we can do those experiments in parallel with everyone else who wants to use this Large Hadron Collider at the same time, it's clearly the time to get started. So let's move right away to designing our experiment. So the first thing we're going to do is we're going to gather various measures of sector performance, their momentum, liquidity, volatility, pricing, trends, historical ranges of prices. We're going to want to normalize that data, perhaps into log space. We're going to adjust the ranges of the data to prevent outliers from squishing our data into buckets that prevent them from being distinguished from each other. Then we're going to use unsupervised machine learning to identify key features that have existed in market days previous to this. Then we're going to use unsupervised machine learning to cluster those and identify what days are most similar to each other. And then we're going to take this model, feed it back into Kensho, and we're going to ask, what will happen the next day? So let's recall our hypothesis. So now we're going to take a moment to ask you to log out of your retirement accounts. While machine learning is amazingly powerful and amazingly cool, I'm an engineer, not a financial advisor. Don't day trade your retirement account. So the first thing I said we were going to do is we're going to gather and normalize our data. We do this in a compositional, API-driven fashion that is powered by Google Cloud Platform. In this case, we take a configuration and we inject it with time series information, event from our knowledge base and our event almanac, measures of price and momentum and liquidity. And behind the scenes, we're going to normalize and clean up that data. I said this would just be the good parts. This compositional style of machine learning means we can leverage all that Google has to offer in one notebook. In this case, I'm pulling in almost 4,300 days of market data with about 64 features for every day. So we love matrices. And so do computers, and so does machine learning models. In this case, we're using single value decomposition to remove redundant data. I'm not helping the computer very much here. This is the computer telling me, hey, I found some stuff you really didn't need to include. It's not that valuable. And in this case, SVD says, I can remove a chunk of your information and still keep almost 98% of the distinguishing characteristics. I'm asking the computer literally to say, what can I throw away? The next thing we're going to do is throw this into a model called tsne. In longer form, it's T-distributed stochastic neighbor embedding. This reduces the dimensionality of the data from 64 dimensions down to 2. But it does not preserve the state of the data. It is helpful for plotting it in a human understandable space. But I do want to emphasize in just a couple lines of code, I have told the computer almost nothing. I'm challenging the computer to tell me. I'm going to continue to be very lazy. I'm not going to pick or estimate the number of clusters that we should use beforehand. I'm not going to make assumptions about the internal data structure. Affinity propagation essentially says what information is passed from previous states in the data to future states. And the computer will figure this out on its own. As we layer these clusters in two-dimensional space, the silhouette score will give us essentially what it sounds like it is, an overlay of the data, and to what extent do the shadows or silhouettes of those clusters overlap or fit with each other. Now, a terrible fit would say, I'm in a cluster, but I really belong in some other cluster. And a great fit would say, I'm so happy in my current cluster, I would never want to be anywhere else. It's not even close. And the scores for a silhouette range from -1 to 1. In this case, we have a 0.15. We're doing OK. I've seen better. We can continue to improve it. So let's visualize this in 2 dimensions. So this is a pretty graph. There's some larger areas where a lot of days appear similar. There's some tighter clusters that seem to be really close together. Now, Kensho deals so much with historical precedents that for me, I'm drawn to the clusters that have a lot of days. This allows me to go back and measure things that have hundreds of days in similarity. But taking a moment that I've already learned something here. I can go pluck out clusters that only have 2 in them or 3 days in them. And just the fact that these days seem to be so distinguished from all the others can make them notable as well. If as the market day rolls on, I find the most similar days are one of these tiny clusters that seems to not be similar to anything else, that can potentially be valuable information all by itself. So as the computer starts organizing and sorting your data and giving you perspective on what is common versus uncommon, it gives you the power as a human to make a judgment about, is this rare? And if it's rare, what do I do? Or maybe it just sounded rare, and now the computer is telling me, no, this happens all the time. We ran into this with the drop of price of oil. We went from about $140, dropped to $100, and there was a big discussion around that, because a $40 drop in oil is enormous. But is it? And we were able to use Kensho to show that it wasn't an unusual event. It wasn't a buying opportunity. there was room for it to drop, because on a percentage basis, oil dropping 20 or 30% was not uncommon. And as the summer went on, oil dropped to $70, to $60, and more recently, it was down in the 30s. So just the quantity and how rare something is valuable by itself. So let's look at a specific day. And in this case, I have chosen February 23rd, so about a month ago. This particular cluster has a couple hundred precedents in it. And in this case, I'm looking at other dates, and I've bucketed them by month. In machine learning, as the feeble human who's participating in this task, I find histograms immensely useful, because it gives me a sense of the shape of the data, how it's laid out, how the computer has organized it for me. And then I can look at this and say, that's interesting. So what's interesting about it? Well, for one, I see there's a lot more days like February 23rd more recently. It's a chunk in 2014 and 2015. I don't see much in 2010, 2011, 2012. Little spike in 2008. Not much in 2007. And then I go back into the early aughts. I see there's more clusters of data. And intuitively, I find this makes sense. The regime of the market from the financial crisis to about 2014 or early 15 was a long, steady march up to the right. It was recovering from the Great Recession. People's confidence was going up. The stock market was, earnings were strong, right? Revenue growth was strong. The housing market was showing signs of recovery and stabilization. There was a quantitative easing program going on that helped fuel this progress. And then as we approached the 2015 window, people started to think maybe the federal government is going to start unwinding quantitative easing. People's confidence started to rebound. People started to talk a lot more about jobs, right? So it says to me that perhaps this machine has learned something about the structure of the market and the overall tone of the sectors and how they behaved with each other as it changed from leading into the financial crisis to the financial crisis to recovery from the financial crisis to now. So what I want to do is I want to take a moment now to feed this into Kensho, and we're going to ask what happens on days like February 23rd. Can we switch to the demo? No? Cool. So we're not a hedge fund. We put out a website. We sell our product to major financial institutions. And what I've done here is extracted the dates that the machine has told me are similar. I have fed them into our analysis engine. In this case, I have 256 previous dates. Again, you can see the histogram of how they are clustered by days. So I'm going to ask the system a very specific question. If I buy on the close of days like February 23rd, and I sell it the next day, how do I do? So I'm literally taking, on February 23rd, I see we're coming into the close, right? The markets are open from 9:30 to 4 o'clock. Coming into close, say it's 3:30 in the day, and I look at the stock prices, I look at my portfolio, I look at what's going on macro levels, I look at how the sectors are performing, I look at what's in the news. I run and I ask the machine, what days are like today? And the machine has told me I found more than 250 precedents. I'm going to say, if I were to buy, if this ends up being just like how I think it's going to shape up over the last half hour of trading, what should I buy? Or if I'm already holding it, maybe I should sell, reduce my risk, reduce my exposure. In this case, I'm just going to do some liquid ETFs, materials, energy, consumer discretionary, financials, technology stocks. The results, we can analyze what happens on all of those dates. We compute on the fly more than 85 different statistics, from beta-adjusted returns to p-values to your actual raw or average daily returns. We adjust for dividends, corporate actions. You can see the dispersion in how the various market sectors pan out. There's not tight clustering around those events. In this case, I'm looking at the beta-adjusted return. This helps normalize the performance of the various sectors relative to the benchmark. So I'm looking for outperformance or underperformance rather than just maybe everything went up on that given day. So what happens? So in this case, I'm going to treat this returns chart as a stack rank. And it seems like in this case, energy has historically outperformed. Materials is up there. You have down at the bottom, XLF is the financials. I see healthcare seems to underperform. So in this kind of thing, I might say, hey, let me look at my holdings. Am I overweight healthcare? Should I do something about that? If I was planning on buying energy, should I buy it today rather than tomorrow? And lastly, we give our customers all the raw data output. We run tests, t-tests, both one-sided, two-sided, depending on the scenario that you're trying to measure, about looking for fat tail risk and looking for shifts in the distribution of returns. We also look a lot about time series. So the way machine learning teaches us about time series, we then feed that into a visualization that allows us to appreciate what the machine has identified and overlay that with how the market has performed. So I do it. I'm going to say sell healthcare and buy some energy or hedge my positions on the 24th. So this allows me to do something different. So now I'm actually asking, what happened? I bought some stocks on the close, and now I held them, and here I am on the 24th holding these stocks. So what happened to my portfolio? So I see materials has done quite well. I see energy is still up at the top. I see healthcare has nudged a little bit. I'm not sure if there's something here, but it does seem like the top has generally stabilized, the bottom has generally stabilized, and there's some shuffling or mixing around in the middle. And it's this kind of thing. I've told the computer almost nothing other than here's some market data, right? Remove what I don't need, group it together, reduce the dimensionality, identify signals that are passed from previous states to future states, and then fed that back into an analysis engine to say, well, this looks like this kind of day, what happens tomorrow? And when I look at this, I say, this is not a random walk. Can we go back to my slides, please? Thank you. Cool. So let's bring this all together. What we're really doing is talking about understanding the connections of things, right? How are things connected to each other? We're statistically annotating the significance of what has happened in the market, right? So we're looking at two market assets. There's a major publicity event, a company has earnings, there's unrest in the Middle East, there's a new product announced by a specific company. To what extent does that influence and alter how that asset performs in the future? Through market assets, that means events happening in the world, news happening now. And to what extent does that change our perception of the likelihood or the significance of events coming in the future? And then lastly, market assets by themselves can influence what will happen as well. And I'll go back again to the drop in the price of oil, where you can see how the drop in the price of oil has caused ramifications in the Middle East around the structure of those governments and their ability to pay their bills. It's affected Alaska, which is now having to start considering income taxes and change their budget economics quite dramatically. And ultimately, through machine learning, we're answering the question, who should care and how much? And if you decide that you do or don't care, right, when? When should you care? When is it important? When is the time to act? And for how long? Now, I got a very interesting question this morning as I was watching the keynote, and the person next to me asked me about machine learning and said, is this a biological process, or is this a mathematical process? I think that's a fantastic question. Because at the top level, machine learning, neural networks especially, they behave like a biological process. There's layers to them, there's nuance, they incorporate new things. As new data comes in, you can incrementally train your model in the same way that a child discovering a toy or gravity or getting to visit the Large Hadron Collider incorporates new information into its already existing perception and knowledge of the world. But if you zoom in to the micro details of the model, you're trying to back out, does this machine really get it? Did it really find stuff that I can't see? And you look at the individual layers of the model, it starts to look like math. It is math, right? It's matrices, it's numbers. And you can peel apart the layers of, say, a neural network and say, at each layer, what does it know? And how does this change what it knew from the previous layer? In the same way we might test a child in school to say, what did you learn this year? And compare that to how they did the previous year. And this is our brains as well. We think of our brains as a biological process because they are, right? It's lots of connections, it's flaws. We learn something, we unlearn it later. But then you zoom into the micro detail, and our brains are firing neurons. It's ones and zeros. Did it fire or not? And so when I look at how we've analyzed the connectedness of things in the world, the increasing velocity at which information comes in, we rely increasingly heavily on the computers to process this information, like the prodigy that it is, at a velocity that I can't match. And it tells me things. And that allows me to delete code, replace it with models that learn and update, and then go back to solving my customers' problems. Thank you very much. I can do some questions. I have about 10 minutes if people would like to ask questions. Yes?
Yes.
For designing today is similar to what they did in the past. What data?
Oh, so the question is, what data did I use to decide what was similar in the past? In this particular model, I was using pricing, volume, volatility, ranges, moving averages, various ETFs representing various sectors. There's a lot more stuff that you can pull in and layer increasing nuance on top of these things. For example, you might, one thing we frequently do is we'll pull in when earnings and other major shock level events will affect an asset. The volume of ETFs has increased and varied over years, so you probably want an ARIMA model that normalizes some of the seasonality out of those things. There's additional information. I probably could have picked additional sectors if you want to study something at a macro level. Rather, in this case, I was looking at something that was very US-centric. So one of the things we find very valuable about being able to run rapid experiments in the cloud is you want to pull in more data, we can scale up the computers to do that. If the experiment seems not to be fruitful, we throw that away. We didn't have to build out a huge infrastructure and then scurry around trying to get teams to make sure they're always utilizing it. The second part is it allows us to study sample sets, and then if it looks promising, then we scale up the project accordingly. So I think the big thing is the compositional style allows us to inject different features and different data and play with that. And then when we find something, we can iterate on that.
A question.
Yeah.
Have you tried feeding this model with historical data, but omitting some of the significant, days, and see if your model could have predicted those?
Yeah, so that's a great one. So the question is, can you essentially do a in-sample, out-sample test? So you take, say, 80 or 85% of your days, you train on that data, and then you use it as an out-of-sample test on the other 15 or 20% of the data. In this case, I think you'd want to pull in additional features in order to do that well. So please don't trade this strategy. But at the same time, that's exactly the right thing to do. And the other nice thing we have, because we have this complement of machine learning and back-testing analysis, we're able to check those things. And then the incremental layering of machine learning allows you to constantly incorporate new information to be like, what did I miss yesterday? Let me incorporate that. What did I get right? Let me reinforce that. And so the model of learning is very much fail quickly, do again. But machines, unlike maybe humans, don't develop like a bias. We don't get hurt. Our feelings don't get hurt, right, if you're constantly wrong. Computers don't get discouraged. And then their velocity of running experiments so fast is such a multiplier that they're able to fail so many times until they get it right at a scale that none of us can match. Microphone.
So did it predict February 24th?
I think it got some things right and some things wrong. In that, I think the general, if you think of it as like layers of sediment, the things that were generally doing well historically were generally toward the top, and things that were doing poorly were generally toward the bottom. But I think you'd again want to, like, I wouldn't go trade your retirement account based on that. And I think there's more you could layer in there. But yeah, I think in general, like, it seemed to have some sorting there, and a sophisticated financial investor would probably look at some sort of weighted strategy that would buy some things in a higher ratio or short other things or sell things in a various ratio to potentially hedge or leverage opportunity.
Did it identify any days that it never happened?
So the question is, did it identify any days that had never happened before? Yeah, so there was a bunch. What I did in terms of, so we have a precedent engine, right? So we use machine learning to identify precedents of when something has happened like this. And if there aren't many precedents, then you really can't run a test on what has happened before, although it may be valuable to know it hasn't happened. So when there are small clusters, I just basically threw out ones that had, I think it was just a handful of days in them, because I don't have a robust statistical way of feeding those back in to do analysis on those. But certainly, say, if I had a dashboard up that tells me, going into the close, like, hey, this looks kind of unprecedented because of these reasons and why, that's something that, at the scale of information coming into the system, no individual could do. Microphone, yes.
So the Python code you showed is written inside the browser, and that would trigger your machine learning library on Google Cloud Platform. Is it?
Yeah. So the question being, so we do so the question is about coding in the browser using an IPython notebook. So we love APIs, we love services, we love compositional services. So one of the things we do is we build our own services, our own models. We use Google's services and Google's APIs. And then that allows our data scientists to work in an IPython notebook, and that essentially serves as a journal of what this is, and they can pull things in. And if the experiment doesn't work out, we can stash that in a Git repo, and someone can pick it up later, or at least learn from that. So the way we do this is we have an API, I didn't show it here, that we can kick off analysis in the background and pull those back in.
So instead of Google's TensorFlow-based machine learning framework, you manage all your own machine learning models and libraries?
We do both. I got just a couple more minutes.
Right here.
Yes.
Have you applied your model to other data sets? I'm just curious, as an experiment other than financials.
Yeah, so we've certainly played around with it. We're very much focused on financial information right now. The financial industry is heavily focused on security. They have very high standards for robustness, throughput. They have large-scale data, which keeps it interesting. There's clients, there's an immediate hunger, like answer now, and I think that has a lot of analogs across many different sectors and data sets. We ingest a large variety of data, so it's not just numbers from market data, but we also do world events, news. We have unstructured data that we parse out and do entity identification and to kind of tease out what's connected. We feed a lot of that into our knowledge graph so that we can understand the connectedness of things. Like proverbial, you could like shake the knowledge graph and see what else shakes and for how much and over what amount of time. And our knowledge graph has object-oriented structure to it that allows us to validate things, and a lot of those annotations are time-related because we love mapping things to time series. Allows us to throw into matrices and do machine learning on it. Microphone. Oh.
When you're talking about doing machine learning, you're working with historical data, but in the past, there were no other companies doing machine learning on data in the early 2000s, 1990s. So how do you say that your model is valid compared to historical data when all the financial institutions are doing this kind of analysis now?
Sure. So there's so the question being that lots of people are doing this, and I think it's true. For example, Google's been doing this for quite a long time, right? And I think a big chunk of machine learning is knowing what to pay attention to and letting the computer advise that. And I think a lot of what's going to revolutionize the finance industry and many other industries as well is they're going to move to the cloud. They're going to use machine learning to remove code. They're going to use machine learning to analyze data. They're going to do it in near to real time. And then the humans will be enlightened as a result of that. So it flips the teacher-student relationship, right? As an engineer, I'm so used to basically spelling out a recipe for the computer. Do A, then B, then C, or call A and then call B on that, or call C on that. And this flips the relationship. So now it's rather than a couple people trying to teach a lot of machines, we basically say, here's the framework and data for the machines to learn, and then they will teach us. And that, I think, is an immensely powerful paradigm switch that flips everything. There was another question back there? Or? I got 2 minutes. Last one.
I had been playing with Watson, and the ability to actually type in a question, and then it understands the semantics of what you're asking, or the context of what you're asking, and gives you an answer. Have you built any of that into your product, and have you leveraged any of Google's machine learning algorithms to do that?
Yeah, so we love natural language processing. I think it's a very intuitive way. Search is a very powerful tool for us and for the financial industry. We have a query engine where you can type in more free-form questions. Where I think it becomes exponentially powerful is I shouldn't have to ask the computer. So we're evolving from a world that says, computer, what about this? What about this? What about this? And it behaves like hunt and peck. And we're coming to a world where we say, no, computer, just let me know when it's important, when I should care, for how much, and how long. And so I think they both play off to each other. The other area where we use a lot of NLP is on the ingestion side to identify things, and you can use hidden Markov models to pull out structure and implications without even necessarily needing entity identification. So there's a lot of cool stuff coming out there, and Google's a major leader in that area, especially on the text side. All right, last one. Yeah, so the question is, do we sell the final product, or do we perhaps sell pieces of it? And the answer is we do both. So we're building a platform that is very flexible, has many layers to it. We can scale separately. We follow the Google GCP model of microservices and being able to expose those to have the right layer of abstraction, and we potentially open those up as they become ready. So, cool. Thank you so much, everyone.